Hey everyone, and welcome to this explainer. Today, we're stepping into what I like to call the next level of science. When you're younger, science is really all about just being curious, right? You're outside observing the world around you, maybe looking at bugs or watching how water flows. But now we're moving from simply observing things to actually figuring out exactly how they work under the hood. We're going to learn how basic observations lead to precise measurements, how we build models of reality, and how we actually test our big ideas. So grab a seat because today is all about building your very own Science Explorers toolkit. But before we start building that toolkit, here's a massive question we have to answer. The natural world out there is huge. It's incredibly complex, and honestly, it can be pretty chaotic. So how in the world do scientists figure out the rules of the universe without getting completely overwhelmed by all the tiny, confusing details? Seriously, how do we make sense of a world that has literally millions of things going on all at the exact same time?
Well, let's dive into this by mentally grabbing the first two tools for our kit, the magnifying glass and the compass. Think of the magnifying glass as a symbol for careful observation. It reminds us to slow down, pay close attention to patterns, and notice those tiny things we might otherwise just walk right past. The compass, on the other hand, reminds us that exploration needs actual direction. We can't just wander aimlessly hoping to stumble on a scientific breakthrough. We need to ask the right questions and point our ideas in a specific direction if we want to find the truth. Okay, so this brings us to our very first, and honestly, maybe the most absolutely crucial concept to grasp today, the model. Because nature is way too complex to study all at once, scientists build models. Now, when I say model, I am not talking about a little plastic toy airplane. In science, a model is a simplified way of looking at a real system. Scientists intentionally ignore useless details to keep things simple. For example, if a physicist wants to figure out how fast a massive, complicated car is moving down the highway, they don't draw the engine parts or the cup holders. They might literally just draw the whole car as a single tiny dot on a piece of paper. Because for that specific math, a dot works perfectly.
Let's test this concept out with a really fun challenge directly from the text, example 1.1. Imagine you're playing a cricket match, and you absolutely blast the ball high into the air. You want to build a scientific model to answer one simple question. Will it cross the boundary for a 6 without hitting the ground? Now, think like a scientist for a second. Out of everything happening on that field, what details do you actually need to figure this out, and what can you completely throw away? To figure out if that ball crosses the boundary, we have to make strict choices about what to keep in our model and what to ignore. We absolutely must keep the mass of the ball, the speed of your hit, and the direction it's flying. If we have those three things, we can do the math. But we completely ignore the brand of the bat, the bright red color of the ball, or how much grass happens to be growing on the field. Now, what's really interesting here is that throwing away information isn't a mistake. It is a deliberate superpower. It clears the clutter and helps us find the answers simply and quickly. Let's try applying this superpower yourself with Activity 1.1. I want you to imagine you want to model a bicycle ride from your school to your home, just to calculate exactly how long the trip is going to take. What details would you intentionally ignore? Well, just like the cricket ball, ignoring the shiny color of your bike frame, the brand of your tires, or the cool stickers on your helmet makes your math a whole lot easier. They literally don't matter to the clock. You just focus on the distance of the road and how fast you are pedaling. And this idea of simplifying things brilliantly illustrates how some of the greatest minds in history work. Take the famous physicist Meghnad Saha, for example. When he wanted to understand giant, complex stars burning in the night sky, he didn't try to track every single tiny atom or complicated chemical reaction happening inside them. That would be impossible. Instead, he simplified. He treated the entire star as basically a giant ball of hot gas. By ignoring those ultra-complex details, he was able to easily connect the star's color to its temperature. But here's the catch. To share these amazing models with other scientists around the world, we need a precise, shared scientific language. We have to use standard units, like kilograms and meters. If we don't, absolute disaster can strike. There's a famous story of an airplane fuel miscalculation that proves this. An aircraft ground crew confused pounds with kilograms when they were measuring out fuel. Now, because a kilogram is much heavier than a pound, the number they read meant they didn't put nearly enough fuel into the plane. The result? It literally ran out of fuel midair. Standard units ensure everyone across the globe is on exactly the same page. And another huge part of our shared scientific language is math. Now, I know, sometimes math can seem super intimidating. But please don't let math scare you. Equations are not just annoying obstacles you have to memorize for a test. They are incredibly compact, helpful guides. Think of an equation as simply a sentence, written in a special language that describes exactly how things like distance, time, and speed are related to each other. Once you learn how to read it, math is just a powerful tool for thinking clearly. Okay, let's move forward and see how our understanding actually builds as we gather all these mathematical observations. In science, we organize our understanding into three big categories: laws, theories, and principles. A law describes a regular pattern we see over and over again, like Newton's laws of motion. If I drop an apple, it falls. A theory goes deeper. It explains why those patterns occur. And remember this, in science, a theory isn't just a random guess you make over breakfast. It is a heavily tested explanation backed up by massive amounts of evidence. Finally, a principle is a broad idea, like the conservation of energy, that just helps us make sense of specific tricky situations. With our laws and theories in hand, we get to use another amazing tool in our kit: predictions. Let's look at example 1.2 from our text to see how this works. Imagine a girl named Varsha looks up at the sky and says, "It will rain this afternoon because the clouds look dark." Now, that's a guess. It's a decent guess, but it's still just a guess. How can her friend Meghna jump in and transform Varsha's simple guess into a real, scientifically testable prediction?
Well, the crucial point is that Meghna needs to ask questions that look for measurable evidence and past patterns. Instead of just glancing at dark clouds and shrugging, she can ask, what is the exact humidity percentage today? Was it over 80% the last time it rained? What is the wind speed? Is the temperature dropping exactly like it did before the last big storm? Good scientific predictions rely on real data, not just simple yes or no gut feelings.
So, let's take a moment to pause and ponder. I want you to take a second and think about a prediction you or your family made recently. Maybe you were watching TV and predicted who would win a big cricket match. Ask yourself, was your prediction based just on a gut feeling, like, oh, I really like this team? Or did you look at the evidence, like the players' past scores, the current weather, and the condition of the pitch? Applying scientific thinking can massively improve the predictions you make every single day. And this habit of scientific questioning is also exactly how we bust fake viral myths. Have you ever heard the claim that eating food during a solar eclipse is somehow harmful to your body? Well, put on your scientist hat for a second. An eclipse is just a play of shadows. It's the moon blocking the sun. So ask yourself, does the shadow magically create a toxic chemical reaction that spoils your lunch? Does the temperature drop enough in 2 minutes to ruin food? No. By asking simple, testable questions, we can confidently say that claim is totally false. All right, let's pull out our final physical tool from the toolkit: estimation. Estimation is the superpower of building an intuition before you sit down to do the hard math. For example, if you want to know how much rice a family needs for an entire month, estimating helps you realize that 100 grams is way too little and 3 tons is ridiculously too much. It gives you a vital reality check to make sure your final answers make logical sense before you commit to them. Let's try this together with example 1.3. We are going to estimate how many liters of air you breathe in a single day. Now, before we do the math together, I want you to guess a number in your head right now. Go on, pick a number. How many liters of air do you genuinely think go into your lungs over a full 24 hours? Okay, got your guess? Let's walk through the estimation steps like true explorers. Step 1. When you're just resting, you take about 12 to 15 breaths a minute. Let's say 15 to make it easy. Step 2. There are 1,440 minutes in a day. If you multiply those, it means you take roughly 20,000 breaths daily. Step 3. How big is one single breath? Well, think of blowing up a standard 2-liter party balloon. It takes about 4 breaths to fill it. So one breath is roughly a quarter of that balloon, which is 0.5 liters. Now for the grand finale. We multiply our 20,000 daily breaths by our 0.5-liter estimate per breath. Half of 20,000 is 10,000. That means you breathe a massive 10,000 liters of air every single day. Did you guess anywhere close to that? Probably not, right? But here is the cool part. Even though we didn't measure every single breath perfectly with a machine, we can be highly confident in this huge number because our rough estimation steps made total logical sense. Time to pause and ponder again. Consider this. Why is an approximate estimate a fantastic tool for planning how many sandwiches to bring on a family picnic, but a genuinely terrible idea when filling a commercial airplane with jet fuel? Think about the consequences. Sometimes close enough is absolutely perfect and saves you time. But sometimes, like when you're flying thousands of feet up in the sky, you need the exact, precise, down to the decimal scientific value. Now, as you advance in your studies, you are going to see science split up into different classes at school, like physics, chemistry, biology, and earth science. But here is a little secret they don't always tell you. Nature does not care about these borders at all. In the real world, these divisions simply don't exist. Solving real, everyday problems requires mixing all these branches of science together into one big team. Look around you right now for our final pause and ponder. Just pick any object in the room, maybe the mobile phone you're using to watch this, or a pressure cooker sitting in the kitchen. Try to spot how at least two different branches of science had to work together to make it exist. A mobile phone isn't just one science. It needs physics to make the electronic touchscreen work. And it relies entirely on complex chemistry for the battery inside to hold a charge.
Or take something as simple as a surgical mask, which we all became very, very familiar with recently. To make a mask that actually protects you, you need physics to create a special electrostatic attraction that traps tiny particles. You need chemistry to actually manufacture the polymer fibers the mask is made of. You absolutely need biology to understand the exact microscopic size of the virus you are trying to block. And you need math to model how the air flows through it when you breathe. All the sciences team up to keep us safe.
As we wrap up, I want you to remember this vital quote from our reading. No scientific theory is ever final and none is beyond a question. This is so important. If our models or our predictions completely fail, scientists don't get upset and just rely on stubborn belief. They don't ignore the facts. They rely on evidence. They go right back to the drawing board to figure out what they missed. This amazing openness to being wrong and learning from it is actually science's absolute greatest strength. So, there you have it. You now have your very own Science Explorers Toolkit. You know how to build simplified models to cut through the chaos. You understand the precise language of standard units and mathematical equations. You know how to make testable predictions based on real evidence. And you know how to estimate your answers to give yourself a reality check. The whole universe is out there waiting to be understood. The only question left is, what will you point your compass at next? Thanks for exploring with me today.